So let's start with Unit 9, Thermochemistry. A couple of big ideas that you have to understand is systems in nature tend to go towards lower energy, so let's go with green, and higher entropy. So easily said, however, there's this word here called entropy. Simply put, for high school chemistry, we like to call entropy this chaos. Or disorder. In the thermochemistry world, it has a more intense definition where they're talking about in a closed system. It's basically the measure of the amount of energy that's not available to do any work, but we're not going to talk about that. Talking about a closed system is ultimately talking about a system where you have a regulation of the system that you're talking about and whatever the chemical reaction that's occurring within it. So for all intents and purposes, you see this word entropy for high school chemistry, know that it means disorder. So you can think of it simply as you in your bedroom. Okay, if you're in your room, let's say 7 days, you decide that you're just going to go in there to sleep, you're going to have quite the mess by the end of the week. Okay, unless you put some energy into it. So if you're constantly picking up after yourself, putting that energy in and picking up your laundry or taking the food out of the room or, dusting, at the end of the week, you're not going to have as much work to do. Or you're not going to have as much disorder, which is entropy. You can also consider systems as nature to have this inverse relationship. So if I lower the energy, I'm going to increase the entropy. The second main idea that you have to know for thermochemistry is that energy is neither created nor destroyed. It's really only transferred in a chemical process, meaning that in order for certain things to occur, there's energy that's either required to start it or to be given off at the end of it. We can usually measure chemical processes by the amount of heat lost, and heat is technically not lost. It's lost by the substance and given off into the environment. So let's talk more about this word heat. Heat, also known as thermal chemistry. This is the energy of motion, so we also call it kinetic energy. Okay, and we can measure heat. Heat is usually an average taken of the energy of most of the atoms in a sample. We do that. We take that quantitative measure by taking its temperature. And for the most part, heat moves from hot objects to cooler objects. Okay, we know this when we touch a stove. If it's hot, you touch it, you can feel that heat, and the heat is actually transferred to your skin. Same thing when you're taking a temperature. The cooler object is usually the thermometer. If you have a temperature, that heat is being transferred to the thermometer and being measured. Temperature is usually measured in degrees Celsius when we talk about chemistry. Okay. In some cases, when like physics and the like, you might see Kelvin. But for all intents and purposes for this class, we're going to work in degrees Celsius. Energy itself, which is the ability to do work, is measured in joules. And you can see that when you look at table D in your reference table. So let's take a quick look. Energy, work, quantity of heat, joules. Okay. So that's how we're going to be measuring energy at this time. So taking a look, there are a couple of equations that you might need to know. The equation that we're looking at is for heat. So if we go to our reference table and we go to page 12, okay, we can see heat here. And we have three different definitions, okay, because there can be other influences that affect how we measure this heat. So these three different equations we'll be looking at throughout the course of this unit. And luckily they tell us what each of these variables are. And as we go through the notes, we'll see how heat is transferred, how heat is manipulated or can be affected by the materials, the change in temperature, and the mass of something. We'll also look a little bit at water and how water changes from different physical states. fusion and evaporation, respectively. Okay. And just to take a quick look, we went over this at the beginning of the year, temperature. We need to be able to convert between Kelvin and degrees Celsius, so we might have to revisit that as we do our math in thermodynamics. So back to our notes, we have a couple of different equations. Let's start off simply, okay, with Q equals mass C and delta T. So we call this Q equals MCAT. Even though this is not an A, that's the delta sign. So Q is heat, M is mass, and the specific heat of water can be found in a special place in your reference tables. On that first page, here's what you're going to have to look at. We're mostly talking about water in chemistry, so we're going to need to know the amount of energy it takes to change between a solid and a liquid, and we also need to know the amount of energy it needs to change from a liquid to a gas. Also, the specific heat of water, when we bring this up first, is that you're not going to know right away. Well, what is the specific heat of water? Okay, so this, you have to memorize that this is the C factor. So this is the C they were talking about. That specific heat of water, the variable is called C. So when we look at this, okay, it's important to use the equation when we're talking about degrees Celsius. Note that the delta T, which is this part, is the final temperature minus the initial temperature, or you can just say that it's the difference between it, but it's not going to be a negative or a positive, so to speak. Okay. And you have to be able to recognize, well, when am I going to use these equations? You're not going to know unless you really write down what variables you have, and then you can be able to choose which equation you would need based on what your variables are. So when do you use this equation? When you see a specific heat of water, or something to do with water, or if you see a change in temperature of water. Those would be the keys to indicate whether or not you would use that specific heat equation. So let's look at example 1. How much heat is released by 7 grams of water when the temperature changes from this to this? And then the second follow-up is it absorbed or released? So let's do this together. We see a change in temperature, so I'm going to use my Q equals MCAT. So how much heat? We don't know. We have our mass, which is 7 grams. We have our change in temperature, which 15 minus 10 is 5 degrees Celsius. But we're missing C. But are we? We know that C can be found in our reference tables, and that's going to be 4.18 joules divided by grams Kelvin. So let's go back, write down our 4.18 joules per grams times Kelvin, and we're going to input it. So Q equals 7 grams times 4.18 joules per grams times Kelvin times 5. And when we do the math, all multiplication here, we're coming up with roughly 146 joules. And we know it's joules because we could go through the math and be like, well, that's going to cancel. Okay. Since Kelvin and Celsius are on a similar scale, meaning it's a 1-to-1 scale, we could convert this to degrees Kelvin, but the difference is still going to be the same. So this would cancel. Okay. So we can call this K, or degrees Celsius. So that's going to cancel, and we're left with joules. Now the key to this is to be like, okay, how much heat is released when its temperature changes from 15 to 10? So we have to think of this. If there is a change and there is a release of energy, we call this exothermic. And we can see that it's exothermic because it says released. We show exothermic using the symbol negative. So anytime we see a negative delta H or anything negative when it comes to heat, it is automatically implied that it is exothermic. Okay. So on the flip side, we can look at this as, well, if we see anything positive, that's going to be endothermic. And we'll go through another table on your reference tables to show you how you would be able to identify exo and endo based on its positive or negative denotation.